Good afternoon, esteemed guests and distinguished colleagues. My name is Rupak Kern, and I'm a Ph.D. candidate recently in the Department of Plant and Soil Science, working with Dr. Wanjan Go in the Tropical Physiology and Precision Ag Lab. And I'm also the president of the PSS Grad Council. So it is my honor to introduce you today to our keynote speaker for this PSS Spring Seminar 2024, Dr. Gary Marek. Dr. Gary Marek is a research agricultural engineer and the lead scientist in the Soil and Water Management Research Unit at the USDA-ARS Conservation and Production Research Laboratory at Bushland, Texas, where he manages the unit's large weighing lysimeter facilities. His research interests include measurement of crop water use for sprinkler and subsurface drip irrigation system, scheduling and the soil water sensor, remote sensing, and crop and hydrological modeling. So please help us welcome Dr. Gary Marek to share his insights and expertise with us today. Thank you.
Thank you for the invite. I'm happy to be here. Anytime we get to share information about the weighing lysimeter project, we like to take advantage of that. Just a little bit of background about me and how I got started in agriculture. I was raised in Amarillo, Texas, went to high school here, and was fortunate enough to go to school at West Texas A&M, and then even more fortunate to start a career in the region. So a lot of folks, when they introduce themselves, they'll show you a map of the world, and there'll be a bunch of squiggly lines of how they moved all over the country, all over the world. Well, I don't have that map because mine's essentially a dot. But I've also argued that rather than teach somebody from outside the area, where there's always good to have somebody outside the area, but it's also nice to have somebody that grew up in the area. So already familiar with the regional issues. I started in irrigation work really early on, right out of high school. I actually managed some of the weather stations that were used in the Texas High Plains ET network. Many of you may be familiar with that. And then after graduation, I actually moved into waste management, manure management, carcass composting, and air quality monitoring, particulates in beef cattle feedlots with Texas A&M AgriLife Research. And then following graduation with my Ph.D., I was fortunate enough to get a postdoc with the lab at Bushland under Dr. Prasanna Gowda. And I started working in ET again in high school. And some of the summers I worked on these actual lysimeters as a 20-year-old. And then, so it's kind of been full circle for me to be a scientist in the same unit that I worked in all those years ago. So we'll get started here. So first, what is evapotranspiration, or ET? It's commonly defined as the combined evaporation of water from land and plant surfaces and the transpiration through plant surfaces. In other words, it's crop water use. It's how much water the crop uses. So what is a lysimeter? There's a couple of different definitions I've pulled from the web. One from Wikipedia they're cylindrical containers filled with soil, which can be used to study the transport of water and material through the soil. Nowhere is it written that a lysimeter should or must be cylindrical, so that's a little bit odd to me. Another one from Merriam-Webster was a device for measuring the percolation of water through soils and for determining the soluble constituents removed in the drainage. Again, one definition, but not in the context we're using them in. The one I found that I like most was from Edaphic Scientific, and it states, a lysimeter is a device or apparatus that measures water movement in the soil, edaphic or vadosome. The definition of lysimeter is muddied and has come to mean many different things. Today, the word lysimeter cannot be used in isolation and is usually a compound noun. And I would wholeheartedly agree with that statement. Again, in our context, the compound noun is weighing lysimeters. So a weighing lysimeter is a device used to measure the actual ET of a plant by measuring the weight of a plant soil and container over time. So why do we want to do that? I'll go into some history of the weighing lysimeters at Bushland, but their primary charge was for the development of crop coefficients to be used in irrigation scheduling. We also measure ET to determine crop water productivity, to evaluate irrigation systems and management, and also to evaluate indirect ET estimation methods. So why weighing lysimeters? If you go to the internet today, or you're a researcher and you want to measure ET, the most common thing you'll find, or piece of research equipment you'll be pointed towards, is the eddy covariance system. They have their place. They may or may not be accurate. They're not a direct measurement of ET. And some of the work we've done early on shows that their uncertainty and their error values can be high. So, and I've highlighted properly designed and managed weighing lysimeters remain the most accurate method for direct measurement of ET, and they're largely considered the gold standard for ET measurement. Again, the primary motivation for the construction of the Bushland weighing lysimeters was to determine crop coefficients for the region. The project was headed up by Terry Howell. So I'll start with just an outline of what I'll present today. First with the history and purpose of the lysimeters, design and installation, management, data collection, and then some QA/QC that we do on data that we measure. And then some later alterations to the lysimeters, including conversion of the east fields to subsurface drip irrigation. Summarize some of the archived data and how those data are becoming available to the public now. And then some modeling efforts, simulation modeling efforts, and then also current and future research. So again, I mentioned Terry Howell. Terry Howell was the father of the lysimeters at Bushland, Texas. He had worked in Fresno and California in ET, and he wanted to build lysimeters in Bushland. So prior to doing that, he sent a 3-man team to tour lysimeter facilities across the U.S. There were some in Northern and Southern California, New Mexico, the Coshocton lysimeters in Ohio. I believe there were some in Nebraska. So the idea there was to see what's out there, see the designs, maybe what they liked about some of them, what they wanted to improve on, and then come up with an ideal set for Bushland. So in the pictures here, my dad, Thomas Marek, was one of the principal designers of these lysimeters. Little did I know at the time that I'd be working on them, 30-something years later. But there's the soil tanks there are shown in the upper picture. I distinctly remember on a weekend going in there and seeing those being painted with epoxy coated painting again. So it's kind of a full circle thing for me. The first ones, most of this work was done in-house, which is something I don't think we could ever get done today with the bureaucratic red tape, the safety issues. Just we don't do things like this anymore in research. And obviously there's an opportunity cost here. I mean, if you've got a crew that are building these things, there's research that you're not doing. So a lot of them were built over the winter. The first ones were installed in 1987. I think there's 4. The last one was completed in 1989, I believe. So the soil at Bushland is a Pullman clay loam. They're soil monoliths ranging from about 1 meter to 1.5 meters. We have a calcic horizon, which can act as an impeding layer for water infiltration until it's saturated. Some lysimeters can be reconstructed based on the surrounding soil, but at Bushland we could not recreate that, so that's why they were taken as a monolith. The lower picture there shows the soil tank. You can see the little dirt berming around it. There was actually excavated a little bit larger than the size of the lysimeter, which were 3 meters or 10 feet by 10 feet by 8 foot deep. And then there were piers with the poles there, and there were hydraulic jacks. So that soil tank was actually pressed into the ground like a giant cookie cutter, raised out of the ground with a crane, flipped over. The fine sand drainage base was put in, a drainage system, and the bottom was welded on it. So again, the drainage system was installed. Bushland has had a long-standing relationship with Campbell Scientific and their CR7 data loggers. We were one of the first test beds for those, for the load cells that measured ET in these. And then neutron probe access tubes, 2 in each lysimeter, were installed. So here's a little bit more about the installation. You'll notice in the top picture the excavated pit. So what you're looking at there is the room that's below grade that houses the soil tank, and then just to the side there is the entry hatch. So you'll notice that opening at the top is larger than the soil tank in the background there. So that tank, once it's fitted, it's lowered into that, and then there's a top piece that's welded around the top of that, just a little bit wider than the soil tank. And then when it's all covered up, you end up with this very unassuming picture in the bottom, where when you walk up on a lysimeter, you're like, oh, here's the weighing lysimeters, and there's really not a lot to see unless you go down inside. But there's the idea there that the soil inside the tank is representative of the field outside, and then the access hatch is shown there below. So the location, it's a 48-acre field, approximately square. It's divided into 4 quadrants. and they're designated as the lysimeter. There's a lysimeter located in each one of these fields in the center, and they're designated by the cardinal points, northwest, northeast, southwest, and southeast. So when the time they were put in until 2012, the two west fields, the northwest and the southwest, were managed as dry land plots, and then the two east fields were irrigated, and they were serviced by a 10-span lateral move irrigation system. And then immediately to the east was a grass reference weather pin. It's a well-watered, clipped fescue surface where we had our meteorological tower at 2 and 10 meters, and that's where we calculate our reference ET. And that was a part of the original focus for the lysimeters, is that we would get our reference ET values from that grass plot. We would measure ET in the lysimeter fields for various crops, and then by division, we would come up with the crop coefficients. So a little bit about the management. I mean, it seems fairly straightforward, but there's actually an army of folks that manage these and have managed them for the last 35 plus years. In the upper picture here, you'll see us at planting. So obviously, our fields are GPS planted. So rows are very straight, and then they're centered on the lysimeter box. Obviously, we can't drive the tractor across the access hatch there. So what you see pictured there in the upper picture is the rows. You can kind of see there's some stakes in the rows at the corners, at the edge of the box, and then some in the foreground here and some past the hatch. We back the tractor in, we line it up as best we can, drive out that east side, do the same thing on the west side, and in between those and across the box, we measure across the box and use stake and strings to get the rows lined up there. And that area in between is hand planted for all 4 boxes every year, which is a considerable effort. And we actually double plant the seeding rate there because, again, the field is planted that day or the next day. And we want the crop on the lysimeter to be as representative of the surrounding field as possible. The double seeding rate allows us to ensure that we have enough plants and a stand that's representative of the field. After further crop development, after a few days or a week, we'll take stand counts in the field, and we will thin across this area in the boxes to ensure that seeding population is the same as the field. We do have here, you'll notice the hardware cloth, little tents or teepees across those rows. We've had issues with certain seeds where rodents, for whatever reason, after planting, will go in there and dig those seeds up. And that's problematic because, again, the field is planted. And if we have a problem with germination on the box, we can't go back in time and plant those. So there'll be an intrinsic difference between crop development on the box and in the field. So here's just a picture of what it looks like when it's done correctly and everything goes well. You don't want to see a distinguishable difference between the plants going across the box and the ones in the field. Typically, when we do see differences in some crops, we see a little bit better, quicker plant development in the box, but that usually catches up fairly quickly within a few days. So here is another picture of what it looks like with a soybean crop. There's some IRTs, some infrared thermometers planted in the foreground there. You'll notice the orange flags in the lower left corner there. We also do install energy balance sensors. There's 4 soil heat flux plates, 2 in the inner row and 2 on the plant row, as well as time domain reflectometer soil water sensors. Here's a cotton crop from, I think, 2020. You'll also note that on the back side of the lysimeter there, each lysimeter is equipped with its own rain gauge. And then there's a meteorological tower on the north side of each one that's equipped with wind speed, wind direction, temp RH, and several solar radiation sensors to measure the complete energy balance on each lysimeter. So again, I mentioned the main focus when they were first put in was the estimation or development of crop coefficients. When we measure mass on the lysimeters, it's composite ET. We don't have an empirical way to separate the evaporation from the transpiration. So early on, it was for the single KC method, and you'll see in red there, we determine the crop coefficients dividing reference ET by the crop ET, which in the case is measured by the lysimeters by reference ET. And this is just a conceptual piecewise crop coefficient plot for the FAO trapezoidal shape. See, I'm sure most of you have seen this. Basically, the KCB is the transpiration, and you have your initial crop development, mid-season and late season periods. And your total, or your composite ET is the integration of the evaporation from the crop development period, where evaporation from irrigation, surface irrigation applications are integrated. This is just a generalized crop curve. You typically see this with a dual crop coefficient crop curve. Basically the same thing here, just a little bit more refined. So looking at some of the data, this is typically what we see. This is these are maize years from these are legacy. No, these are hybrid crops. Pioneer 1151. It was grown in 2013, 2016, and 2018. So there's some interannual variation there, but when we try to do 3 years and then estimate that trapezoidal shape for the crop coefficient across there. These are the same data. The top plot is RS, or tall reference crop, alfalfa in this case, and then OS below is the short clipped grass. And alfalfa-based reference ET crop coefficients typically top out at 1.2 or so 1.1, and for short grass reference 1.4. So just a little bit about crop coefficients, some recent work that we've done. Basically taking the FAO and the literature values for crop coefficients, and this was just an exercise that showed the importance of selecting crop coefficients or computing the curvilinear crop coefficient curve for the region that you're in. So on the left, these are from the Manual 70 crop coefficient charts for a temperate climate on the left. Again, legacy hybrids grown in the 90s on the top left, and then the Pioneer 1151, more modern drought-tolerant hybrid grown in the left. And you'll see the book values there, overestimating ET early in the season and then underestimating later in the season. And then the two plots on the right just show we used a Mediterranean climate, and those values from the book match those that were measured and were fitted from the empirical data. So important to note that when you're selecting crop coefficients or crop coefficient calculation approach from book values, that you have the right climate. So I want to go briefly into what the data look like that come off the lysimeters. Each one of those soil tanks weighs roughly 100,000 pounds. They're on an 100-to-1 mechanical advantage agricultural scale, and then they have a counterbalance system. So even though the tanks weigh roughly 100,000 pounds, and we're not interested in the absolute mass, we're interested in the differential mass between a time interval that we're interested in. The mass is actually measured with a 50-pound load cell, and that's how we get the resolution. And that mass is converted to an equivalent depth of water. So over that 10 foot by 10 foot surface, the mass is using the density of water converted to millimeters of water. So on the left axis here, you'll see it could be an arbitrary number, but those are millimeters of mass essentially. And this is what we typically see during the summer on most of our crops. This is the cleanest ET data that we'll see. When you're processing these data, this is the easy part. You have this sigmoidal drop in mass. So again, this is mass. So you see during midnight hours between days, you have relatively flat or low ET values. And then as the temperature comes up, solar radiation comes up, you have increased ET or decreased mass in this case. So when we're calculating a daily ET, we take a midnight centered average from one day to the next. And in this case, for day 230 in 2001, this was cotton, we had 6.5 millimeters of ET, relatively straightforward. Things get a little more convoluted. Here we have irrigation on day 201 or 202 and 205. Having done this a long time, I know we have records for irrigation, but I can look at these lysimeter data. I mean, they're recording continuously. Our base file is 5 minutes, so our mass data is 5-minute averages. So I can look at lysimeter data and for a whole year, and I can almost tell you what increases in mass or spikes like these or discrepancies. I can tell you what happened just because I processed many, many years of these data. In this case, the irrigations are easily quantifiable between the mass at the beginning and the end of the irrigation. And the pink spike there in the middle is a neutron probe measurement. So a student actually walked onto the lysimeter at that point, took neutron probe readings from the two tubes in there, and then walked off the lysimeter, and then you see the plot in blue there, the mass is really relatively unaffected. There's no lasting effect on lysimeter mass. So if we're doing daily calculations, daily ET from midnight to midnight, that spike from that student walking on there has no bearing. But if I was, say I had a satellite pass and I wanted to know what ET was over a 15-minute period or a 30-minute period or an hour period in that data, that spike occurred then, and obviously those data are going to have an issue, and I'll have to look at that more closely. So how we process ET data is really dependent on what you're using it for. Daily is different than hourly. Hourly is different than sub-hourly. When I came on as a postdoc, one of the first things I did was go back through a lot of these data. From their original processing, it was basically a midnight centered mass subtracted from the next subsequent day. And if there were any events that happened, whether it was maintenance, neutron probe readings, an irrigation, or a precipitation event, those days were just thrown out. But we were looking at doing crop modeling, and those models want continuous data for ET. So we were looking at a way to adjust these data for those days where we had precipitation or confounding events on the lysimeters. And that was largely a lot of my postdoc work. So this is just an event, and it was a spreadsheet approach, and it was largely manual. So what we would look at the ET data for east or west field. In this case, it's the northeast at the top, letter A, and then the southeast, letter B. And they're managed the same. And you can see that those two plots, those are two different lysimeters, are fairly repeatable. And then you'll notice in the middle plot, there's precipitation from the rain gauges at each lysimeter. And they verify the spikes that you see on day 202 and 204. Or sorry, you can't see that very well. 212 and 215. And so we quantify those irrigations and we subtract that amount from the mass plots. And then the two plots in green at the bottom are kind of our check. So we've adjusted for those increases in mass, and that should be that sigmoidal plot that we talked about. That's kind of how we verify that we've processed the data right. This is painstaking. For the first 3 months I was a postdoc, I did this every day, 5 days at a time, all 4 lysimeters for 10 years of data. Paul Kalasi, who works in our lab, is actually working on an AI-based approach to automate this. So we're working through those kinks right now, but it is, going back to the archive data and doing this was labor intensive. And here are just some examples of some other confounding effects we'll see. We do see dew. This is earlier in the year. So you have air temperature, the diurnal variation, and then like day 108, you can see in the morning hours, we have accumulation of dew. And typically we don't see it as much during the growing season when it's hotter in the summer, but we do see it earlier in the year. And this brings up a question. As a postdoc, I was unsure what to do with this because, like I showed the first plot where you have this very clean ET and there's not any accumulation of dew, the calculations are straightforward, but what do we do with dew? I mean, dew is technically a precipitation. The environment is such that we're depositing water on the plant. Now we can debate on whether that has a real effect on the plant growth or not, but still in terms of ET, it's a real deposit of moisture on the plants and then it's evaporated. So how do we account for that? And Steve Evett in our lab has published a paper on quantifying dew through the years and quantifying their contribution to the seasonal ET for a lot of our crops. Same thing happens with frost in the winter. We'll have frost that's measurable contributions to the plant and soil surface. And then wind, the wind blows here. So you don't really see this so much when you're on high ET days because the signal to noise ratio is so strong. But noise typically isn't a problem when we're averaging because it's usually centered around a mean of 0. But if you look at some of these days, you can see obviously wind noise in the ET data. And then there's sometimes you come across data, you just don't really know what's going on. In this case, it took some research. This was in the winter, early in the year, end of January in 2001. And what we'd had is that blowing snow, not real wet snow, that had drifted across the lysimeter lip, melted a little bit, and then frozen. So it was imparting forces on the lysimeter that we really couldn't quantify. So in this case, we just lose those data. And I'll mention again, the point of doing the data, most of the data that had been processed in the previous years had only been processed for the growing season. But when we were talking about continuous run models, we needed the off-season data too. So that's where I came as a postdoc. And I can tell you, if you're going to process ET data, you'd much rather process it during the growing season than outside the growing season for these reasons. So again, that was data acquisition, some upgrades over the years. The reason we stayed with the CR7 so long was because of the resolution it had from the analog input voltage channels. The CR1000 wouldn't get the resolution we needed, the CR3000 wouldn't. So most of you know the CR6 came out. Tim Campbell from Campbell Scientific, they were at Bushland in 2016, and they did the first beta testing of a CR6 in one of our southeast lysimeter to verify resolution was at least as good as the CR6. Shortly thereafter, we converted everything to the CR6. And that also made, on our data technician, things easier because we had things like a 2D sonic that obviously couldn't be wired into a 70s model CR7. So we had two data loggers running all the instrumentation, and then there's the issue of matching up the timestamps. So this allowed us to wire all of the sensors into one data logger. Shortly thereafter, like I said, we kind of beat the horse to death there on the crop coefficients. So sometime in 2015, it was decided that we would like to do some studies between subsurface drip irrigation and sprinkler irrigation. So starting in 2013, we converted the west two fields from dry land, moved the lateral move sprinkler over there. So there's sprinkler irrigated. And then the two east fields were converted to drip, subsurface drip, every other row, 1-inch tape. And in the first year, in 2013, the drip was plumbed into the lysimeter boxes on the same zone that the field was in. So when we irrigated, even though we had zones in the field, we irrigated the field at the same rate. So so when we were irrigating, we had water going into the lysimeter box at the same time it was going into the field. And you note that in the top plot here, we have this increase in mass for an irrigation. The problem is a 1-inch irrigation could take, well, depending on the irrigation, it could take 12 to 18 hours for that to go across there. Well, we lose those data during that time because we were adding water to the mass of the lysimeter at the same time we have ET going on. So it's convoluted there. There's no way to quantify the ET. The following year, we updated the two east lysimeters to where they had a separate set of tanks that were hanging from the lysimeter mass itself. So what we would do is onboard all the irrigation that, for like a 1-inch irrigation, we would onboard that volume of water we know. We'd see in the lower plot here, you'd see a one-time spike, relatively quick, in that addition of water, and then a separate pump that was also suspended from the lysimeter, included in the total mass, would begin pumping water at the same rate the field. So we're still irrigating at the same time we're having ET, but that water's already been onboarded, so we're actually measuring ET at the same time that we're irrigating from below. Not sure what all of that means, but that was an improvement. This is a slide that, so everybody always asks, so how much water does SDI save? This is from one of Steve Evett's papers. So this is 2013. I believe this was sorghum. If it's not sorghum, it was maize. But during the early season, I think that may include some pre-watering. We used 85. So the plot in blue here indicates that we use more water on the sprinkler field, and to the negative in red indicates that more water was used by the SDI. So during that early development, 85 millimeters more during pre-watering, and then 53 millimeters during early vegetation development, and that's primarily due to evaporative losses from irrigation when the canopy is incomplete. Kind of a wash there in the middle, and this has always been interesting to me that we used almost more than 3 inches more on the SDI. And in talking to Steve, he believes that's because that was a hot fall that year, and just because the crop that was surface irrigated, there wasn't as much water that reached the rooting zone that the crop could pull upon. So that crop actually went on the sprinkler, went into senescence earlier, but the SDI was able to mine water from lower, and that's where you got the additional water there. So the short answer is, in general, for most of our row field crops, drip on average will save you 10 to 15% in reduced evaporative losses. I can tell you there's some other issues with drip. I never want to misrepresent drip because there are additional challenges to managing drip. When you have leaks in the field, particularly after the crop is up, those are difficult to find. You may show they're there from your pressure, your flow measurements, primarily your pressure measurements. They're difficult to find. Pre-watering can be difficult for drip, and that's not a universal thing either. There's been years where we've had a wet subsoil, plenty of water in the profile, but drying right before planting has prevented water from the surface. In that case, if I start pumping water through SDI, I lose a lot out the bottom. But if I've had a crop that mined the soil water profile the previous year, I can put 3 or 4 inches in this Pullman clay loam and not lose any out the bottom and get water close enough to the top to germinate. But I always counter this by the water savings that we see, let's say in 3 years, in a normal year where we get a precipitation event to germinate a crop, we may lose, or we may give that up in a 4th year to water we've lost to pre-irrigate. So nothing's perfect, right? This is just an example of a study that we just did recently a few years ago. Again, we don't have an empirical way to partition E and T from the composite ET from the lysimeters, but we do have 2 fields sprinkler irrigated next to 2 drip fields. So we had the idea that we could, so long as we didn't wet the surface and they were managed the same, we could use the east lysimeters or the drip as a surrogate for T. So the ET measured from that is largely transpiration because we don't have a lot of wetting from the soil surface from the irrigations. So we compared ET in 2016 and 2018 to SDI. In 2016, for whatever reason, when the lateral move sprinkler was put in at Bushland, we always had MESA irrigation, which stands for mid-elevation sprinkler application, which is a sprinkler drop height around 5 feet or so. It varies. And then there's LISA, which is lower elevation spray application, which is droplets, drops closer to 18 inches or so. So what we compared, so we had the MESA in 16 on the west field and LISA in 2018, and we compared that to a drip field on the east field. And you'll notice in the top plot there, we have a sprinkler irrigation, and then we assume that there's some data from the lysimeters and other preliminary data that the ET rate during the irrigation, which is typically takes about 15 minutes, 20 minutes to get across the box, is negligible or 0, close to 0. So in this case, what we did is we compared days after irrigations, after sprinkler irrigations, and we did the subsequent day as well. And we'd like to go further, but a lot of times just based on our climate and not raining, we'd have to irrigate every 3 times a week. So that limits the number of days you can evaluate. And then the middle plot there shows the ET on the subsequent day, and then you have the rate down at the bottom. So there's an example one during the mid-season in 2018. This is when the crops were approaching plant height, maximum plant height in LAI. So in the middle plot there, the 2 dashed lines are the average, or essentially there's an average there between the 2 subsurface drip irrigations. We only had the southwest lysimeter because it was 100% irrigation, same as the east lysimeters, and the northwest in this case was a 75% irrigation, so we couldn't use it in this study. But we see after an irrigation event that first day, we have a difference of 1.7 millimeters. And then early season, we have incomplete canopy on 2016, on day of year 168, we had as much as almost 3.5 millimeters. So we compared those dates for both years in 16 and 18, and these are the data for 16. So again, going from planting there, and then the maximum LAI and height is the dashed line in the middle of the plots there. So basically the plots, the dots here are the extra ET associated with the sprinkler irrigation. So it stands to reason, and you would suspect this would be the case, but this put numbers to this. It quantified the extra ET that occurred during irrigations from the sprinkler. Obviously, as the canopy started to close, we had less evaporative losses, so that extra ET decreased over time. And then the same thing in 2018, this was LISA again with the lower drops. The same trend, we did have a kind of a little bit of a discrepancy here, and it escapes me the reason for that at the moment. But in summary, we showed that the greatest evaporative losses occur under incomplete canopy conditions, obviously. And those were overall losses are determined by that, and they can be limited to that by the decreased number of irrigations in those periods. But again, if you're in a case where you have to pre-water, especially with a sprinkler, nobody wants to do that. We know we lose a lot of water. We can lose as much as half of that water in a few days, in a couple of days. A lot of times with sprinkler, especially if you're growing a crop like corn, if you don't have that water in the profile when you start, you can't get it past the roots when it's growing, and ultimately your yield can suffer. Again, this is so we did show some differences before complete canopy development in 2016. We had an average of 2.1 millimeters of extra ET for the sprinkler, with the highest value being 4.9 and the lowest 0.1. And similarly, we had 0.6 was the average after complete or canopy coverage. And then for the Lysa in 18, we showed slightly less at 1.9 on average. And then it was same after crop development, full crop development. So the take home here is that you limit your evaporative losses once you get the sprinkler drops below the canopy. Okay, and moving on to modeling. Again, this is where I got my start with the lysimeter data and the lysimeter project. Many of you have probably heard this quote. I can't remember who it's from, but you always hear, "Our model's a good thing or a bad thing?" And someone said, "All models are wrong, but some are useful." And they are an alternative to field research. Research is expensive and time consuming, so the solution to a lot of agricultural problems seems to be modeling these days. But the problem that I have with that is, models require proper calibration and validation, and that's not always done. Just because I calibrate it and validate it for Bushland, Texas, does not mean it may be applicable in other regions. But they are commonly used by regulatory agencies, and they're used in regional water planning. The bottom line here is they do exist and they do get used. So in my view, it's worth improving them. And early on in the lysimeter, like I said, we've been going on 37 years here, but sometime, I guess about 10 or 15 years ago, folks started to notice that these data were piling up, and that, they're basically being held close to the vest at Bushland. There had been some incidents where folks obviously had collaborated with us at Bushland, or researchers at Bushland. Most of those have been good, but there were some instances where folks would take the data, maybe not understand them, misapply them, or more problematic in that they wouldn't cite the data or cite the source or the scientists that were involved with that. So it kind of went from where we let some of this data out, and then they went back from that. But the way USDA is now, those are publicly available data. They're paid for by tax dollars, so over time they are being disseminated. And the modeling efforts are really what kind of put this forward, is because it's a tremendous data set, not only from the ET and the water management and the irrigation data, but on each one of those fields, every 2 weeks we take plant height subsamples from the fields and from the boxes, and we take destructive leaf area index samples from the field. And we also have, in each one of those fields, there's 10 tubes outside, neutron probe tubes for soil water analysis that are in a square pattern 4 and 8, and those are compared to the lysimeter box, the data from the lysimeter boxes, to verify that the soil water conditions in the box are the same or approximate those in the field. So just to summarize some modeling efforts, again, there's a tremendous amount of data, not only the ET, but the irrigation, the neutron probe, agronomy records, fertilizer records, the biomass, leaf area index, and yield samples. We've worked with several collaborators over the years. There's some listed there. My first work was with the SWAT model, soil water assessment tool. And it was basically to determine if SWAT could reasonably estimate ET from some of the lysimeter data that I first started working with. And we found that it could. But what we found out later, and I still need to do work on this, is we were able to force some factors in the model so that simulated ET matched measured ET. But not looking at the soil water data at the time, And going back and looking at that, that caused some discrepancies in the soil water. So again, you can get the right reason in modeling for the wrong answer. The other work that I've done is in DSAT with some of the full and limited irrigation maize data at Bushland. I think a generalized statement that holds true for most models is that we can get them to behave fairly well for fully irrigated deficit or fully irrigated data sets where we don't have fertilizer or water stress. But as soon as we start introducing particularly water stress, most of these models break down or they have issues there. Sometimes that's able to be remedied and sometimes it's not. So other models that we've used data and efforts for are the EPIC Apex model, which is closely related to SWAT, the root zone water quality model, aqua crop, and the cotton 2K model. So the lysimeter data are great. I've talked about how many there are and what we do to make sure they're as good as they are, but they're not perfect. So one of our problems is standardization of files. So like what we look for in sampling data for maize is way different than what we do for cotton. So it's hard to standardize those files. Peripheral treatments, there are fields around us. There are producer fields around us. So particularly with cotton, folks aren't supposed to spray, 2,4-D, but we have this last year, we had 2 or 3 incidents where we know we have drift that came across there and burned the top of our cotton. There's really not a lot we can do about it. Just make notes to it. Sensors do have issues. We have a full-time support scientist who monitors the data coming off the lysimeters every day. If she notices a problem, we'll go out there. Sometimes it's a communications problem. Sometimes it's a sensor itself. Try to have backups for all those and get those replaced as quickly as possible. The masts are problematic in some way, particularly for herbicide or pre-emergent applications. It's difficult to get back into there and spray around the box and get that application the same as it is in the field, just because of the start and stop of the way the sprinkler delivers herbicide. And again, the quality control and QC is a continuous process that we're continuing to evolve and develop. The remainder of the slides I have are largely borrowed from Steve Evett. We presented this in the ASABE second ET symposium in Penn State. And this is that thrust from USDA to get these data out to the public. So the archive data from the lysimeter, they're hosted on the USDA-ARS National Library Ag Data Commons. So there's a link there. And the easiest way to get to the Bushland sets are searched by Steve Evett. Steve has led the charge in getting these data into publicly available format. It's just some metadata. There's geographic coordinates for everything that we've done, where everything is, conventions, symbols and abbreviations, and then obviously his specialty is soil properties by depth and horizon. The weather pin data from the adjacent short-clipped grass weather pin are available. Those are 15-minute average. And again, they include solar radiation, wind speed, air pressure, temperature, and humidity. And there's duplicate sensors for all of those. They are QA/QC'd to each other, but you can pick one that you feel like better than the other. There's usually not a lot of difference between them, or you could take the average. And then also the soil water content data. Soil water content during the irrigation season are taken in both fields every week. And those are quantified to soil water in the rooting profile. So again, lysimeter data is a 5-minute average, and you can integrate those into any interval that you want to from there, whether it be sub-hourly, hourly, daily. And that includes the water balance data, and all the agronomic data is also included. And the biggest challenge in this is getting it into their template on the Ag Data Commons, which is pretty rigorous, but once you do the first one, it's not too bad, he tells me. So again, I appreciate his efforts in doing this, but there are spreadsheets, they're in columnar format, they're machine readable, readily available. So some of the data that are available are the alfalfa data sets from 96 to 99. I was actually a student during that time, and those data where we grew alfalfa on the lysimeter fields was used to verify the ASAE's, standardized reference evapotranspiration equation. We have maize from several years, soybean from several years, sunflower, winter wheat. There's some older cotton data that will be coming available soon, and we've gotten 3 years of cotton from about the last 5 years that we'll be publishing soon or be posting soon. We're waiting on the scientists in the lab are given the opportunity to publish those data before they're publicly available. Again, so cotton's coming. More sorghum data is in process right now. And then we did do forage sorghum in 2006 and 2007. I mentioned most of these data have been used in several evaluations of models. Most notably, the AgMIP, the Agricultural Model Intercomparison Project, had previously used data from Ames, Iowa. In this last iteration, that paper's out. It was used data from Ames, Iowa, again from EC Systems, and then also Bushland data for maize. So current research, again, a lot of our focus is on the difference between SDI and DRIP. We only have 4 lysimeters. It's only one field, N equals 4. It's also our largest fields on the irrigated fields on the station. So we try to stack, I guess would be the word, where we collaborate with other folks or other scientists in there to take advantage of that water use and in those facilities. Some of the projects we're working on now are evaluation of TDR soil water sensors to estimate ET. We actually have some of those installed in one of the Northeast lysimeter soil core. And we did some previous work with scintillometers. We had 2 different ones. We had an infrared, and then we had a laser scintillometer with mixed results. And then we had a postdoc do some preliminary work with eddy covariance several years ago. Again, showed some large variations in error. Typically, you hear errors in EC are related to advection, and where heat moves on to those from the surrounding fields. But these fields were designed to be large enough to where that's supposed to be minimized. So this last year, we had 2 modern EC systems, one on the northeast, one on the northwest fields, and we're currently evaluating those data right now. So we're trying to put to bed, or I guess quantify the differences we can see between eddy covariance systems and lysimeter measured ET in a semi-arid environment. And we also have a UAV program. I've worked a little bit with Sean on hope to work more with him on getting that up and going. I'm finding that really needs a dedicated scientist to do that, but I have a technician who's made some headways on, we have been flying multi-spec and thermal imagery of the lysimeter fields over the last 2 or 3 years, and we're hoping to glean some information from that. And I would be remiss if I didn't mention that the lysimeter project is a team effort. Terry Howell headed this up for several years, and after his retirement, Steve Evett did, and I worked close with Steve Evett. Steve has moved to in the position of lab director, so he's, I guess, relinquished his management hat of the lysimeters. So I've been managing the lysimeters the last year and going on now. But it is an army of folks. Some are listed there. Most notably, Karen Copeland, who is our soil scientist, but also our instrumentation support scientist, and then Bryce Ruthhart, who helps me with all of the field agronomy operations. And we're really blessed at Bushland because a lot of these folks that were here when these lysimeters were put in are still there. And I think that's the downfall of a lot of lysimeter projects, is that they start out, somebody comes in and they're good for a few years and then they get promoted or they move on, and then there's no continuity in operation. So very fortunate. I mean, there's a long list of lysimeter projects that were up and running for a few years and did good things, and then they're still sitting there today or they were removed. So people always ask, well, we need more lysimeters, and I would argue maybe we do, but it's not, and they're expensive, especially the ones that put in like this. But it's not that upfront cost. It's that maintenance cost of these folks, the manpower that it takes to keep them going and to keep them at high quality. So there's just some acknowledgments and disclosures, and I'll end with that. So take any questions you might have. I think, and I'm not sure EC is the answer, but I think it's a question worth answering, is from a management aspect, for irrigation scheduling at least, is EC viable in a semi-arid environment before. I think it's valuable to quantify those error rates. And let's say that they're, like, I have data that I need to be working on right now from this past year. I have 5-minute ET data. So I can say on average, the error rate, let's say, I'm just saying it, maybe it's 20%, but because I have the 5-minute data, I have the sub-hourly data, when is it close, when is it not? And maybe we can learn some things about, the atmospheric conditions that have been, conducive to AC being accurate versus non-accurate. And that may lead to, better EC systems, better ET sensing technology.
Thank you for the clarification. I have a question regarding crop rotation. Like if we have the intercropping system, the crops are planted at the same time, so they might start their reproductive and stage at the same time. But if we have the relay cropping, the two crops are planted at different times in the same field. So one is at the vegetative, one is at the reproductive. So they have different crop coefficients, they have different water requirements at that particular time. So how we can approach for the irrigation schedule?
So if you go to the literature, the crop coefficients are based on that planting date, right? So when they had the Texas High Plains ET network, and there's a couple different methods where you use a single approach, the trapezoidal shape, or there's a newer approach for the curvilinear approach. Crop coefficients are region specific, they're crop specific, but they're also planting date specific. So the time starts from that one planting for that one, and then that time would start for a separate one for that second planting date. And in a lot of the ET networks, I don't know about the modern ones, but the former High Plains ET network would list for where you were. If you subscribe to it, you'd say they would have an online, it used to be a fax, but then it was a online sheet that would say wheat and then list 2 or 3 planting dates. And then every day it would calculate the crop coefficients for you. And what was the second part of your question? The first part, it triggered something to me that I forgot.
We have like two crops, like wheat and soybean in the field. The wheat we planted in November and soybean we planted in January. But both are at the same time. One is at the later stage, wheat is at near the maturity, and soybean is at the early stage. So both have different crop coefficients at that particular time. So how we can schedule the irrigation?
Well, you'll have to have 2 separate irrigation schedules. You can't water the field. I mean, yeah. Well, that's, my short answer would be you're going to waste water on one of those depending on which one you irrigate towards. And to your earlier question, I think one of the things, all of the crop coefficient work that was done previously was under fully irrigated conditions. So we wanted that max, right? So if you look at the crop coefficient functions, there's that KS, the stress term. So, and we know it's lower than that. And we can calculate those, we can estimate those. But one of the things I want to do going forward, and they've been hesitant to do this in the past because we can get our soil water out of whack, but deficit irrigate some of these crops. I mean, we're running out of water, right? Not a lot of guys are going to fully irrigate corn in bushland. So they just don't have the water to do it. So one is to investigate alternative less in water intensive crops, one of which being cotton. And with the influx of dairies, even though it's localized, there's a lot of water that's being concentrated to grow forages for dairies. So we're actually looking at, through our Ogallala Aquifer program, limited irrigation forages, including alfalfa, where we irrigate early on to get a first couple of good cuttings and then keep it alive for the rest of till the next year. But again, empirical or measured stressed crop coefficients, I think, is something that needs to be done because there's not a lot of empirical data for those.
So, last question. Let's do it quick. I'm afraid we may have some starting to block in a second.
So with the open ET stuff that is coming out, with all the outburst data being taken, along with some of the lysimeter data from Bushland, what are your thoughts on using the open ET for the
I'm mixed on that. Initially, I've been hesitant to provide data to that, and then I was just on a conference call for planning for the Ogallala Summit that's coming up in Kansas, and one of the people brought up a point on there that data from OpenET is being used, and it was an online article where groups of farmers were being compared to other groups and saying these guys are using twice as much water as these guys. So it's like, on one hand, you see the benefit of the tool, but on the other side, there's always, it can be used in a bad way too, so.
Okay, thank you, Gary.
Thank you, guys.